Everyone see this all right? Okay, perfect. So great to be here. This is really exciting. I've heard a lot of great things about this course, and it's really cool to be able to offer sort of this alternative perspective in computer-aided synthesis planning. Like Sarah said, I've really been interested in this area since I've started my PhD here at Berkeley. And what I hope to do today is sort of offer a bit of a complementary perspective on how computational tools can be really useful in the context of complex molecule synthesis, and where some of these techniques succeed and where they sometimes have limitations when we try to apply them to problems that we care about. So I've sort of organized the lecture today into sort of four generally main sections. I wanted to sort of roughly or loosely organize it according to how we think about a synthesis workflow, right? When we start from picking a target and finally we end up with a finalized, optimized route, how computer tools can sort of insert themselves into every stage of this process. And this is sort of how I wanted to organize things today. So at first, we'll spend a little bit of time talking about target selection and some of the considerations there and how that informs how we use computer aided synthesis planning tools. Next, we'll spend the majority of the time sort of in this center section talking about how retrosynthesis algorithms can be really useful for generating different ideas or route plans. And then once one has a series of different routes, talk about how these tools can help us prioritize and sort of de-risk different synthesis plans. And then finally, we'll talk about how computers can help us in the sort of validation and optimization phase of synthesis planning, going into the laboratory and actually trying these things experimentally. All right. I guess there's a question. Can people see my mouse, or should I turn on the laser pointer here?
We can see your mouse.
Okay, perfect. Great. Okay, so jumping right into target selection, I just want to briefly say a thing about sort of why we make molecules in the first place, right? And I think what we expect out of computer or sort of computational tools for synthesis really does boil down to our motivation, our justification for why we're endeavoring in synthesis in the first place. And I think there are sort of two main camps into why we make molecules, namely strategy and sort of function. So on the function side of things, it sort of makes sense that if a molecule has really interesting biological activity, that might merit its synthesis in the laboratory, right? Maybe we want to make it to sort of study its structure-activity relationships, or if it were an API, perhaps we wanted to learn how to make it on large scale. And this can really sort of set the foundation for what we consider to be a good route or a good disconnection in a synthetic strategy. On the other hand, a lot of complex molecules have high strategic value. And in endeavoring to make these complex molecules, one often has to innovate new creative strategies for making these complex molecules, whether that's investigating a sort of biosynthetic hypothesis or sort of exploiting things like symmetry or topological disconnections. This can sort of teach the chemistry community something new from a strategic perspective on how to make molecules. And so just a couple of examples, you probably have already spent a little bit of time thinking about steroid biosynthesis, right? But for example, there's this classic paper from Bill Johnson in the late 60s, where one can take these sort of linear polyenes and through a Lewis acid catalyzed polyene cyclization, end up with these sort of steroid scaffolds, which have been very interesting. So, if you want to investigate a biosynthetic approach, strategy sort of plays a lot of roles here. On the function side, you can imagine, again, right, if you want to access something on really large scale, this sort of is another justification or motivation for synthesis. In this case, just this last year, this paper from Merck, where they figured out a way to make molnupiravir, this sort of anti-COVID antiviral compound, from really cheap starting materials from uridine in 5 steps that are really scalable and have good overall yield. So I just sort of want this in the background. We think about our motivations for synthesis can influence how we use these tools. Okay, so I want to spend the majority of time today on sort of these central 2 sections, sort of idea generation phase and route selection phase of the synthesis planning workflow. And I want to start just by talking about retrosynthesis. And I know this is really foundational to everything that's been sort of taught in this class, and you've probably heard this a lot at this point, and it's very intuitive if you're, doing total synthesis in the laboratory. But I want to sort of reframe the whole process of retrosynthesis essentially as an algorithm, a conceptual algorithm since that's, really what it is. It's a workflow for how we systematically think about building molecules in the sort of backwards way. And so, step by step, just to walk this through, the first step of retrosynthesis, right, is to think about all the different possible disconnections of your target. And this is typically done via our own learned knowledge, right? We've all taken sophomore organic chemistry. We have a sort of our own learned database of all the different possible organic transformations. And we sort of apply these when we think about pattern recognition, when we look for retrons in a different target. At this stage, once we've generated lots of different disconnections, we now have to sort of consider which of these disconnections is the best. Which bond should we break first? And the sort of way we prioritize all the different possible disconnections is typically done through some kind of strategy, right? So if we're interested in a biosynthetic proposal, we might be more biased towards disconnections that seem to test that hypothesis directly. Or if we want to take advantage of a really convergent approach, we might want to break bonds that sort of get us to that point of convergency the fastest. Once we've generated sort of our prioritized disconnections and we've drawn our precursor, we then have to ask the question, right, are these reactants commercial, or can they be made from commercial reagents? So, we do SciFinder searches. We try to figure out, is this something close to what's been made before, or is this something that, is in the Aldrich catalog? And if the answer to this question is no, which for the first few iterations, it usually is no, we then repeat this retrosynthesis process until we arrive at a point where we actually do have something that's commercial or known in the literature, at which point we end the search algorithm and we compile all of these into a route. And if we have multiple different routes, we might evaluate them according to different strategies that we have in mind, again, just like we talked about. So this is sort of how we as humans think about retrosynthesis, right? And maybe it comes as no surprise that computers do much the same thing. When we program retrosynthesis algorithms, this is very much in analogy to how we as chemists think about retrosynthesis. But there are some interesting subtleties, right? So instead of this step here, where we are sort of generating different disconnections according to our own ingrained knowledge of organic chemistry, a computer has to do this via a database. It only knows what you program it and what you teach it. So a computer has sort of its own conception of reactions. And we'll talk a little bit about some of the subtleties there as well. But it has to be taught organic chemistry one way or another. For the next stage, when it comes to which bonds are best to break and how to prioritize different disconnections, computer programs are going to do this through something called a scoring function, where it can sort of rank which disconnections maybe reduce molecular complexity the fastest, or are the most strategic according to what it's been specified in the program. It has to ask the question, are these reactants commercial? And it typically does this through kind of a commercial database like Millipore Sigma. And at the end, when it has to rank different routes, it also does this through a scoring function. So we'll talk a little bit about how some of those scoring functions work. Now, just a bit of history in terms of sort of the original retrosynthesis program. This was something that came out in the late 1960s, and it was called LASA, which stands for Logic and Heuristics Applied to Synthetic Analysis. And perhaps it comes as no surprise that the original retrosynthesis algorithm, the original retrosynthesis program, was developed by none other than E.J. Corey. And it's sort of interesting that someone that has become so famous, right, for codifying these synthesis rules, and I know some of these have been covered in this course specifically, was actually really pioneering in the realm of computer-aided synthesis planning. And sort of an interesting fact is a lot of the work that was done by Corey and his team in sort of codifying these logical rules for synthesis, right? What became sort of the foundation for the logic of chemical synthesis was really motivated by trying to figure out how to teach a computer which is a strategic bond to break. And so, a lot of that development came out of preparation for trying to teach this computer how to break down molecules in retrosynthesis. So it's a really interesting interplay here. I think computer-aided synthesis planning and just in general, applying computer tools to synthesis really causes us to sort of think deeper about some of our own fundamental questions and sort of get our own house in order before we try to apply these two automated tools to our workflows. So LASA's program was really sort of rudimentary, but I think it was really ahead of its time. It had this graphical interface for sort of non-coding users to be able to draw in their molecular structure, and the computer would kind of interpret it from there. It contained sort of a database of reactions that it was taught explicitly. These were sort of hand-coded reactions, and while there weren't very many, the number did sort of steadily grow to about 2,000 different reactions by the 90s. And unlike a lot of the sort of modern variations of retrosynthesis algorithms today, LASA was very chemist guided. So it required a lot of intervention and handholding by the chemist user at every step in the algorithm. And so it wasn't sort of automated route generation. It wasn't going to tell you anything you didn't probably already know as a chemist. But it was sort of a really pioneering feat nonetheless. Since LASA, there have been a whole slew of retrosynthesis programs that have been developed since then. Sort of before the 2000s, in addition to LASA, there are all these programs shown here. I won't sort of spend a lot of time on each one, but you might recognize some of these names who are sort of formidable figures in synthetic organic chemistry. Sarah told me that in this class, you've talked a little bit about Hendrickson's work in strategy as well. So it's also very interesting that, those that have a lot to say about synthetic strategy are also very interested in applying this towards computer algorithms as well. A lot of these programs were primarily academic in nature, and they haven't really been sort of upkept since then. I think most of these has kind of died out, unfortunately. But since the 2000s, there've been kind of a rebirth in this field. A lot of commercial interest has been generated in the realm of retrosynthesis programs, particularly when it comes to industry and how medchem teams can sort of be assisted by retrosynthesis routes that are generated by computer. So one of the big players in this area is this program Chematica Cynthia, which we'll spend a little bit of time talking about. This was developed by Bartosz Grabowski in Poland, and then later licensed to Millipore Sigma and sort of rebranded as Cynthia. Another big player in this area is C-CAS, which is a program developed by Connor Cooley and Klaus Jensen at MIT. This is sort of a machine learning based program, which has a lot of different modules, and it's sort of free and open source. So it's really accessible for us to try. We'll do a little bit of a demo looking at how this program works in real time. So hopefully if you're interested, you can sort of check that out later. IBM has a play in this space, AstraZeneca, and perhaps it's maybe no surprise that large databases of reactions like SciFinder or Reaxys have their own sort of retrosynthesis program as well. Okay, so now I want to sort of talk about each stage of this retrosynthesis program, sort of ask the question of how do computers do this under the hood? We'll sort of take a peek at some of the subtleties at every step in this process. So first, how does a program like learn organic reactions in the first place? And I think it's sort of very analogous to what we all probably did, right? As sophomores in organic chemistry, we made flashcards. We made these types of templates where we tried to commit to memory that if a Grignard comes together with an aldehyde, we can do a 1,2 addition and make a secondary alcohol. And as humans, this is kind of intuitive. This is how we explicitly commit to memory these different reactions. And of course, there's a little bit more annotation required when it comes to a computer, right? We have to map all of these different atoms and sort of explicitly keep track of, okay, atom 4 is going to connect to atom 2, and we can sort of map these numerically. And then we also need sort of a list of exceptions, a list of rules associated with each reaction, right? Particularly for this Grignard reaction, we know that maybe protic or electrophilic functional groups are not tolerated, and perhaps you need a protecting group that's required. These are all things that need to be explicitly taught to a computer program because it only knows what you teach it. So these are sort of these template-based algorithms, and there are a couple different ways that these templates are generated typically. These are sort of two camps, or sort of two representatives of two camps. So the Cynthia program I've talked about before, which is probably the most popular commercial option out there, and also probably the most proficient retrosynthesis program, in my opinion. It was originally developed with these sort of explicit reaction template rules. And actually, the way that this database was formed is that Bartosz Grabowski and his colleagues in Poland spent the last 10 to 12 years manually coding essentially these types of reaction templates for 50,000 different reaction rules. So it was a really laborious, sort of painstaking process. And on the one hand, there's an advantage that these were all coded by chemist PhDs, right? They we all have this sort of expertise in organic chemistry. So we have the intuition to sort of know when certain functional groups are not tolerated and when you might need a protecting group. And we can sort of use our own trained knowledge to sort of bake this into these rules. Nicely, each of these reaction templates also typically have references. So if you get a result in Cynthia, you can go look up the relevant reference that might be representative of that reaction type. But as you can imagine, if all of these reaction templates are manually coded, it's not very scalable, and it's tough to sort of keep up with the chemical literature if you have to constantly be churning out new reaction cards to update your model by sort of just paying attention to the literature. So it's not that scalable in the long run. Nevertheless, even though there are, I think, some downsides to this, I would probably say this is one of the best programs out there. C-CAS, on the other hand, sort of tries to take a machine learning approach to the same problem. So instead of coding these templates by hand, Connor Coley and his team basically figured out how to use a machine learning algorithm to extract rules from a large data set from Reaxys or the US Patent and Trade Office. So instead of explicitly being taught this machine learning algorithm just by studying all of the existing chemical literature, implicitly starts to get a sense for what's possible in reactions. Unfortunately, as you might imagine, if it's learning sort of organic chemistry from what's out there in the literature, specifically for things like the US Patent and Trade Office, which includes a lot of sort of industry reactions, it gets kind of biased towards the most common reactions. And so you can expect to see a lot of amide bond forming reactions and Suzuki cross couplings and the kinds of things the industry loves will show up a lot when you train an ML on this database. So that's sort of one of the critiques, I think, of computer-aided synthesis planning for retrosynthesis, is that it's often going to sort of be biased towards what we as academics might call like boring reactions. It's not going to suggest a lot of new chemistry because it will sort of just tend to be biased towards the things that are tried and true in the literature.